Welcome back to Arxflix. Today, we're diving into a groundbreaking paper titled Pivot: Iterative Visual Prompting for VLMs with Applications to Zero-Shot Robotic Control. This research tackles the challenge of enabling vision language models, VLMs, to handle tasks requiring continuous coordinates, actions, or trajectories without fine-tuning on task-specific data. So, let's explore how Pivot works and its impactful applications in robotic control. Here's a snapshot of the Pivot model in action, where tasks are approached as iterative visual question-answering problems. Each image is annotated with visual representations of candidate actions that the VLM evaluates and refines iteratively to zero in on the optimal solution. Traditional vision language models can perform logical reasoning and visual understanding, but fall short when tasked with generating precise spatial outputs crucial for robotic control. The question is, how can these models be adapted to handle such tasks without extensive retraining? The pivot method, or prompting with iterative visual optimization, transforms tasks into a series of visual question-answering iterations. Initially, the image is annotated with a set of visual proposals such as candidate robot actions or trajectories. The VLM evaluates these proposals, and the process is refined iteratively to find the best answers. In simple terms, the goal is to find an action as such that the VLM selects the corresponding label W in the annotated image HOTI as the best fit for the task. This diagram provides a clear visualization of the pivot process: sampling candidate actions, projecting them in image space, querying the VLM, and refining the action distribution iteratively. The approach is tested across various domains: robotic navigation, manipulation from images, and instruction following in simulated environments. Surprisingly, Pivot demonstrates zero-shot control of robotic systems. For example, a mobile manipulator navigates through different environments by refining actions at each step without any specific robotic training data. Here you can see Pivot in action in a navigation task where the robot is asked to find a place for writing, showcasing its adaptive refinement in real time. The performance of Pivot is quantitatively evaluated through various metrics such as success rates, steps to task completion, and precision in grasping objects. Iterative refinement and parallel calls markedly improve performance and efficiency in these tasks. Here is an illustration of a manipulation task where the robot is continuously refining its action to pick up a Coke can, highlighting the iterative improvement. As VLMs increase in capabilities, so does Pivot's performance. The study observed that larger models led to better results, indicating that future advancements in VLMs will further enhance Pivot's zero-shot performance in tasks requiring spatial reasoning. This graph shows Pivot's scaling with different sizes of the Gemini VLM family, demonstrating improved performance with larger models. Despite its impressive performance, Pivot has limitations like handling 3D, spatial reasoning, and fine-grained control in occluded environments. Future work can involve training on datasets encompassing these challenges or incorporating more sophisticated visual representations. This diagram shows performance dips when the robot approaches objects, emphasizing the need for better training data or more advanced model capabilities. To wrap it all up, Pivot takes a significant step toward enabling VLMs to perform complex spatial reasoning and control tasks zero-shot by cleverly using iterative visual optimization. This opens exciting possibilities for applying VLMs in increasingly complex real-world tasks. Thanks for watching Arxflix. Be sure to hit the like button if you found this interesting, and subscribe for more deep dives into innovative research papers. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.